All right then, with 5 electron groups, and remember, we're still talking about situations where these are all bonding groups and no lone pairs. The molecular geometry would be what's known as trigonal bipyramid, which is a complicated sounding name. And that's because this is actually getting to be a fairly complicated kind of geometry. What you have here is 5 electron groups. And they arrange with 3 of the electron groups in the same plane as the central atom. And this part of the molecule is pretty much trigonal planar. But also you have 1 electron group directly above the central atom and 1 directly below it. And in other words, what this amounts to is it's like basically 2 3-sided pyramids stuck together at the base. And that is what's known as trigonal bipyramid. The electron groups in the same plane as the central atom are 120 degrees apart, like they are in trigonal planar. And the ones above and below are 180 degrees apart from each other. And 90 degrees apart from the, basically the, before I go on, I wanted to mention that the electron groups that are in the same plane as the central atom, the ones that are set up like trigonal planar, these are known as the equatorial groups. And the other ones, the ones directly above and below, are known as the axial groups. So we've got axial and equatorial. So the ones above and below, known as the axial groups, are 180 degrees apart from each other and 90 degrees apart from the equatorial groups. What the 2 different names for different positions in this molecule might tip you off that, unlike the previous geometries we've seen, not all of the positions in this geometry are equivalent to each other, even if all of the outer atoms are of the same element. So not all the positions are equivalent. So if you've got bulkier groups, like multiple double bonds or triple bonds, or a lone pair for that matter, they will tend to go to equatorial positions. Because the equatorial positions are 180 degrees apart from each, or sorry, 120 degrees apart from each other, while the axial positions are only 90 degrees apart from the equatorial groups. Okay. Okay, for what they actually look like, the book suggests PCl5 as an example, and that's as good as any, so I'll use that. You can see the, basically if you take 5 balloons and tie them together, you get a shape that's something like this, and that's trigonal bipyramid. If you connect together the furthest point from the center for each of those balloons, you get something that looks like this. And you can see clearly 3-sided pyramid pointing upward, another 3-sided pyramid pointing downward. And you stick them together at the base, and you have a trigonal bipyramid. A good way to draw it on paper is, well, actually the Lewis structure. If you draw it like this, that actually represents what it looks like in 3 dimensions fairly well. But of course, for the Lewis structure, you could have spaced those 5 chlorines any way you like around the central phosphorus. But this is basically the way it looks. We're looking at the trigonal planar part of the molecule going horizontally here, and then the axial positions going directly up and directly down. A model of a molecule like that looks something like this, where you can see we've got the trigonal planar part of the molecule, again, going side to side, and then the axial parts going directly up and down. You can look at it also from other angles. Very often we look at the molecule kind of like this. And with this geometry, you can have some fun with it too. So a little levity to lighten up the mood. The way you can draw it, for PCl5, of course, we've got phosphorus, and we've got 5 chlorines around it. And that doesn't really look much like trigonal bipyramid. And it doesn't. And that's why the VSEPR theory is important. You have to consider how far apart can those groups get in 3 dimensions. And it's not like flat pentagon shaped like you might expect. It's trigonal bipyramid. Something like this. And if you look at this, you can actually see there's your trigonal pyramid right there. And then here is your trigonal pyramid, or sorry, there's your trigonal planar. Here's your trigonal pyramid that points up. And here's your trigonal pyramid that points down. Accounting for my squiggly line there. That's not too bad, I think. Okay, so that's what it looks like. And from this point on, you'll also notice that the central atom has more than an octet of electrons around it. Phosphorus, in this case, has 10 electrons on it. But phosphorus is one of those nonmetals from the third period or below, which can accommodate more than an octet of electrons. It's big enough that they can get far enough apart without any problem. Okay. All right. Okay. The next thing would be 6 electron groups. Okay, so 6 electron groups with no lone pairs. This geometry is known as, molecular geometry would be known as octahedral. And it might not make sense that it would be called octahedral, but actually, when you have 6 pairs of electrons on the central atom, you wouldn't think that it would be called octahedral because 6 and octa means 8. But actually, what this shape looks like is 2 4-sided pyramids stuck together at the base. So 2 4-sided pyramids stuck together base to base. You basically have 4 electron groups in the same plane as the central atom. As you might call a square planar. And also one directly above and one directly below the central atom. Now, why the geometry you get when you have 5 electron groups around the central atom is called trigonal bipyramid, and this geometry is not called square bipyramid, I really don't know. Okay, because this amounts to 2 4-sided pyramids stuck together at the bases. All right, so, and that's called octahedral. And it's called octahedral because it has 8 sides. If I've made a model of one here, you can see that in the same plane as the central atom, you have 4 outer atoms, and one directly above and one directly below. If you take this structure and fill in the sides, you get a 4-sided pyramid pointing up and a 4-sided pyramid pointing down. And in fact, here it is in the book. And you can see here, you got the 4 electron groups in the same plane as the central atom, and then one directly above and one below. If you look at it like this and close in the sides, then of course you've got one 4-sided pyramid pointing up and one pointing down. All right. There we go. So 8 sides. The 4 exposed sides of the upper pyramid and the 4 exposed sides of the lower pyramid. That makes 8 altogether. All of the electron groups in this kind of structure are 90 degrees apart from each other. And all positions are equivalent to each other. The way we often look at it is 4 atoms or 4 electron groups in the same plane as the central atom, and then one directly above and one directly below. But the fact, and that's just a convenient way of thinking about it. Actually, all of these positions are equivalent, and I could turn it around like this, and you could actually end up with the same thing, 4 in the same plane, and one above and one below. I could turn it like this, and you end up with the same thing, 4 in the same plane, one above and one below. I could put the octahedron down like that, and I could flip it over and around and back, and you couldn't tell the difference as long as all the outer atoms are the same. And so that's what we mean by all of the positions are equivalent. If you have a particularly bulky atom to go on one of these positions, it wouldn't matter which one it went on. There's no difference between axial or equatorial. Okay, so there's no axial and equatorial in this. The central atom, again, has more than an octet. And you can see that when we look at an example, SF6, where we have six fluorines around a sulfur. And that doesn't look much like octahedral, but that's because that's a Lewis structure, and so it doesn't really matter where we draw the fluorines as long as we convey that each of them is bonded to the sulfur in the center with a single bond. So that's the Lewis structure. And about the best we can do on paper would be something like this. So you have the ones in the same plane as the central atom, and then you have the ones directly above. And so there's one four-sided pyramid pointing upward, and then the one pointing downward. That's when it gets really complicated. But there you go, there's your octahedral. Actually, that came out better than I thought it would. And that is octahedral. The next thing we have to look at, or actually, if you want to draw an octahedral shape really quickly, you can kind of draw it like that. The next thing we need to look at is what happens to all these geometries if we have some lone pairs. And this is, lone pairs are important because normally when we name the shape of a molecule, we only name the positions where atoms are. So we don't name any positions on the central atom that are occupied by lone pairs. But lone pairs do have an effect on the position of the atoms around the central atom. And so lone pairs affect the geometry, but they don't get named as part of the geometry. So there are now two different types of geometries that we have to keep in mind. There's the electron geometry, which tells where all of the electron groups on the central atom are. And then there's the molecular geometry, which is based only on where the atoms are. So basically, we ignore the lone pairs and name where the atoms are. So I'll write that down so you can get it. Okay, so lone pairs on the central atom will affect the arrangement of the other electron groups. One effect that has is that it can alter the angles somewhat versus the standard shapes. And there's also the fact that lone pairs are not included in molecular geometry. But they affect the positions of bonding pairs, which is where the atoms are. So we do need to consider lone pairs when coming up with molecular geometry. So there's these two terms that we have to distinguish from each other. Electron geometry. And that's based on the arrangement of electron groups, all electron groups, around the central atom. And then there's the molecular geometry. Molecular geometry is the arrangement of bonding electron groups around the central atom. Because bonding electron groups are where you find the outer atoms. And this is because lone pairs are not counted towards the molecular geometry because there are no atoms on the other sides of them. But they do affect the positions of the bonding groups. And it's also useful to notice what the above definitions imply, and that is if there are no lone pairs on the central atom, then the electron geometry and the molecular geometry are the same. So what we've been seeing so far in the examples that we just did with, this number of electron groups or that number of electron groups, what shape will that be? We could have referred to those geometries as either electron geometries or molecular geometries, because in fact they are the same when there are no lone pairs. If lone pairs are present on the central atom, then the electron geometry is not the same as the molecular geometry. And this is the part we're going to focus on now. So we're going to basically see if you have this number of electron groups around the central atom in total, and this many of them are bonding groups, and this many are lone pair groups, then what shape does the molecule take? So that's what's coming up, but that's for the next segment because we're at 30 minutes again.